now at this very second, as you sit there watching this video, something extraordinary is happening to you. Ancient light that has been traveling through the void of space for 13.8 billion years, is passing through your body. It is moving through the walls around you, through the screen you are watching this on, through the very air you breathe. This light was born in an era so ancient, so incomprehensibly distant in time, that when it first began its journey, there were no stars, no galaxies, no planets, and certainly no human beings to wonder about it. This light predates everything you have ever known, everything you have ever seen, everything that has ever existed in the night sky. And here is the part that should send a shiver down your spine. If you were to take an old television set, the kind with the cathode ray tube, the kind your grandparents might have had, and you tuned it between channels so that all you saw was static, that fuzzy, crackling black and white noise dancing across the screen, roughly 1% of that static, that noise, that seemingly meaningless visual chaos, is actually this ancient light. You have been looking at the oldest light in the universe your entire life, and you never even knew it. Welcome, everyone, to what I believe is going to be one of the most profound journeys we have ever taken together on this channel. My name is Here, and if you are new, this is where we dive deep, and I mean genuinely deep, into the mysteries of the cosmos. We do not skim the surface here. We do not give you watered-down explanations and call it a day. No, we go all the way. We go to the very edge of human knowledge, and then we peer over that edge and wonder about what lies beyond. And today, we are going to explore something that I have been wanting to cover in this level of depth for a very, very long time. Today, we are talking about the cosmic microwave background, the CMB, and I know, you might have heard that term before. You might have seen that famous oval-shaped map with the blue and red splotches. You might have a vague sense that it has something to do with the Big Bang, but I promise you, what you think you know about the CMB is only the thinnest surface layer of one of the most extraordinary stories in all of science. Because the cosmic microwave background is not just some interesting astronomical observation. It is not just a pretty picture for textbooks. The CMB is the single most important piece of evidence we have about the origin, the structure, the composition, and the ultimate fate of everything that exists. Everything. Every galaxy spinning in the void. Every star burning in the darkness. Every planet orbiting those stars. Every atom in your body. Every thought in your mind. All of it traces back to what is encoded in this ancient light. Let me give you a taste of what we are going to uncover today. Did you know that the CMB is the oldest light in the universe, and that nothing older can ever be observed by any telescope, any instrument, any technology that will ever be invented, as long as that technology relies on light? There is a fundamental wall in the universe, a wall made not of matter, but of time, and the CMB is the light from that wall. Did you know that this incredible discovery, one of the most important in the entire history of physics, was made completely by accident? By two scientists who initially thought pigeon droppings were contaminating their antenna. Did you know that the CMB is essentially a baby photograph of the entire universe, taken when the cosmos was only 380,000 years old, which sounds like a lot, but is actually an infant by cosmic standards? Did you know that the temperature differences in this map are so absurdly tiny? variations of only 1 part in 100,000, that if these variations had not existed, if the CMB were perfectly smooth and uniform, you would not be here, I would not be here, the Earth would not be here, no galaxy would exist, no star would shine, and the universe would be nothing but a cold, dark, featureless void for all eternity. Did you know that there is a mysterious cold spot in the CMB, a region that is anomalously cold and large, and that some scientists have seriously proposed that it might be a bruise, an imprint left by another universe colliding with ours? Did you know that the light of the CMB started out as visible light, a warm orange glow that filled the entire universe, but has been stretched by the expansion of space over billions of years until it now exists as microwave radiation, invisible to your eyes but detectable by our instruments? These are not science fiction. These are not speculations. These are established scientific findings, backed by decades of observation, analysis, and the work of thousands of brilliant minds. And today, we are going to go through all of it, every single layer, from the birth of the universe through the prediction and accidental discovery of the CMB, into the deep physics of what it shows us, the mysteries and anomalies that still confound the greatest minds in cosmology, and what the future holds for CMB science. By the time we are done today, you will understand the universe in a way that very few people on this planet do. You will understand where everything came from, why it looks the way it does, and what questions remain unanswered. And I genuinely think, you will never look at the night sky the same way again. So let us begin. Let us go back, way, way back to the very beginning, back to the Big Bang. And the first thing I need to do is correct a misconception that almost everyone has about the Big Bang. When most people hear the words Big Bang, they imagine an explosion. They picture some kind of cosmic bomb going off in the middle of empty space, hurling matter outward in all directions, like shrapnel from a grenade. This image is so deeply embedded in our popular culture that it seems almost self-evidently true. But it is wrong. The Big Bang was not an explosion in space. The Big Bang was an explosion of space. And that distinction, subtle as it may sound, changes absolutely everything about how you should think about the origin of the universe. Let me explain. In a normal explosion, a firecracker, a bomb, a supernova, you have matter flying outward through a pre-existing space. The space is already there, and the matter moves through it. But the Big Bang did not happen inside space. The Big Bang created space itself. Space, time, matter, energy, the laws of physics themselves, all of it emerged from the Big Bang. There was no pre-existing void for the universe to expand into. There was no outside. There was no before, at least not in any way that our current physics can describe. The universe did not expand into something. Space itself expanded, and it carried everything within it along for the ride. Now, when we try to rewind the clock all the way back to the very beginning, to what we call time equals zero, we run into a wall. Not a physical wall, but an intellectual one. A wall of ignorance. Because at the very first instant of the universe, we enter a realm where our best theories of physics break down. This is called the Planck epoch, and it lasted for an almost inconceivably tiny fraction of a second. Specifically, it lasted for about 10 to the power of negative 43 seconds. That number is so small that I cannot even give you a meaningful analogy for it. It is a decimal point followed by 42 zeros and then a 1. During this brief flicker of time, The universe was so incredibly hot, so unimaginably dense, so extraordinarily compressed, that all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into a single force. And we have no theory, no framework, no mathematical formalism that can describe physics under those conditions. General relativity, Einstein's masterwork, breaks down. Quantum mechanics, our best theory of the very small, also becomes inadequate on its own. What we need is a theory of quantum gravity, a theory that unifies general relativity with quantum mechanics. And despite decades of effort by the most brilliant physicists on the planet, we still do not have one. String theory is a candidate. Loop quantum gravity is another. But neither is complete, and neither has been tested. So the very first instant of the universe remains shrouded in mystery. It is the ultimate frontier of human knowledge. But what happened after that first tiny fraction of a second that we can talk about with much more confidence? And what happened was something truly wild. Something so extreme, so dramatic, so mind-bendingly violent that it makes every other event in cosmic history look gentle by comparison. What happened was inflation. Cosmic inflation. Not the economic kind, the cosmological kind. In an unimaginably brief burst of time, roughly from 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of exponential expansion. And when I say exponential, I do not mean it grew a lot. I mean it expanded faster than the speed of light. Now, before you object and say, hey, nothing can travel faster than light, let me clarify. And this is a crucial point. Nothing can travel through space faster than light. That is what Einstein's special relativity tells us. But there is no law, none whatsoever, that prevents space itself from expanding faster than light. And that is exactly what happened during inflation. Space itself stretched, ballooned, exploded outward at a rate that makes the speed of light look like a crawl. In that tiny fraction of a second, the universe grew by a factor of at least 10 to the power of 26. That is a 1 followed by 26 zeros. To give you some sense of scale, imagine taking something the size of a proton, something far smaller than an atom, and inflating it to something larger than the entire observable universe today. That is the kind of expansion we are talking about. But why did inflation happen? What caused it? This is where things get theoretical. And I want to be honest about the distinction between what we know and what we hypothesize. The most widely accepted explanation is that inflation was driven by a hypothetical field called the inflaton field. This field had a very peculiar property. It had enormous energy, but this energy was stored in what physicists call a false vacuum state. Think of it like a ball sitting on a ledge partway down a hill. The ball has potential energy. It is not at the lowest point. It wants to roll down. But it is temporarily stuck on that ledge. While the inflaton field was in this false vacuum state, it generated a kind of repulsive gravity, a negative pressure that drove space to expand exponentially. And then at some point, the field rolled off the ledge, so to speak. It transitioned from the false vacuum to the true vacuum. And when it did, all that stored energy was released, and it was converted into the hot, dense soup of particles and radiation that we normally think of as the Big Bang fireball. So in a sense, inflation came before the conventional Big Bang. The hot, expanding universe that most people think of as the Big Bang was actually the aftermath of inflation. Now, inflation does some very important things for cosmology. It solves several deep puzzles that had been troubling physicists for decades. And I will come back to these in detail later when we discuss what the CMB reveals. But for now, let me just plant two seeds in your mind. First, inflation explains why the universe is so flat. Second, inflation explains why the CMB looks almost exactly the same in every direction, even in regions of the sky that appear to be so far apart that they could never have been in contact with each other. These are called the flatness problem and the horizon problem, and inflation solves both of them beautifully. But even more importantly for our story today, inflation did something else. Something that, in my opinion, represents one of the most profound connections in all of physics. During inflation, tiny quantum fluctuations, random, inherent, unavoidable fluctuations that are a fundamental feature of quantum mechanics, were stretched by the exponential expansion of space from subatomic scales to cosmological scales. Microscopic randomness became macroscopic structure. The smallest possible jitters in the fabric of reality were blown up to sizes spanning millions of light years. And those stretched quantum fluctuations became the seeds of every galaxy, every cluster of galaxies, every cosmic structure that has ever existed, including, ultimately, you. I want you to sit with that for a moment. The reason you exist, the reason the Earth exists, the reason the Milky Way exists, is because of random quantum fluctuations that occurred in the first trillionth of a trillionth of a trillionth of a second of the universe's existence. Your origin story begins with quantum randomness at the dawn of time. If that does not give you chills, I do not know what will. After inflation ended and dumped its energy into the universe, we are now in the realm of the hot Big Bang. The universe was a seething, roiling, unimaginably hot and dense soup of fundamental particles. In the very first moments, it was filled with what physicists call a quark-gluon plasma. This is a state of matter where the building blocks of protons and neutrons, quarks and gluons are not bound together, but exist freely in a kind of superheated soup. The temperatures were so extreme, trillions of degrees, that even the strong nuclear force, the force that normally binds quarks together so tightly that they can never escape, was overwhelmed. As the universe expanded and cooled, the quarks and gluons condensed into protons and neutrons. This happened within the first few microseconds. And then something crucial happened, something that determined the entire future of the cosmos. There was a war between matter and antimatter. You see, in the earliest moments of the universe, matter and antimatter were being created in almost perfectly equal amounts. Every time a particle was created, its antiparticle was created too. And when a particle meets its antiparticle, they annihilate each other in a flash of pure energy. So matter and antimatter were being created and destroying each other in a constant frenetic dance. If this process had been perfectly symmetric, if matter and antimatter were created in exactly equal amounts, they would have annihilated each other completely. Every single particle would have found its antiparticle partner, and they would have mutually destroyed each other. The universe would contain nothing but radiation, no matter at all. No protons, no neutrons, no atoms, no stars, no galaxies, no planets, no you, no me. Nothing. But that did not happen. And the reason it did not happen is one of the deepest mysteries in all of physics. For every billion antimatter particles, there were approximately 1 billion and one matter particles. Just one extra matter particle for every billion pairs. A tiny, tiny asymmetry, less than 1 part in a billion. And when the great annihilation was over, when all the matter and antimatter had destroyed each other, that 1 in a billion surplus of matter was left standing. That tiny residue, that minuscule asymmetry, is everything you see in the universe today. Every galaxy, every star, every planet, every atom. You are made of the leftovers of an almost perfect destruction. The matter in your body is the 1 billionth survivor of a cosmic apocalypse. And to this day, despite decades of research, we do not fully understand why this asymmetry existed. We know it must have, because we are here. But the exact mechanism that created slightly more matter than antimatter remains one of the great unsolved problems of physics. There are theories, including CP violation in certain particle interactions, and there are experiments at CERN and elsewhere trying to figure it out. But we do not have a definitive answer yet. Now, as the universe continued to expand and cool, protons and neutrons began to come together to form the first atomic nuclei. This happened in the first few minutes of the universe, in a process called Big Bang nucleosynthesis, and it produced a very specific mix of elements. Roughly 75% hydrogen, about 25% helium, and tiny trace amounts of lithium and deuterium. That is it. That was the entire periodic table of the early universe. No carbon, no oxygen, no iron, no silicon, nothing complex, just hydrogen and helium with a sprinkle of lithium. Every other element that exists, the carbon in your DNA, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of that was forged later, inside the nuclear furnaces of stars or in the catastrophic explosions of supernovae. But hydrogen and helium, the 2 simplest and most abundant elements, those were made in the Big Bang, and the predicted ratios from Big Bang nucleosynthesis match what we observe in the universe with extraordinary precision. This is one of the great triumphs of Big Bang cosmology, and it gives us tremendous confidence that our understanding of the early universe is broadly correct. But here's the thing. For our story today, what happened next is even more important. Because for the next 380,000 years, the universe existed in a state that might seem paradoxical. It was filled with light, more light than at any other time in its history, and yet it was completely opaque. You could not see through it. Light existed everywhere, but it could not travel anywhere. The universe was like a thick, impenetrable fog, a glowing, brilliant fog that extended in every direction to infinity. Let me explain why. At these temperatures, which were still thousands of degrees, the universe was filled with plasma. Not plasma in the science fiction sense, but in the physics sense. A plasma is a state of matter where atoms are ionized, meaning the electrons have been stripped away from the atomic nuclei. The universe was full of free protons, free electrons, and photons, particles of light. And here is the key. Free electrons are extraordinarily good at scattering photons. Every time a photon tried to travel in a straight line, it would almost immediately slam into a free electron and be deflected in a random direction. Then it would hit another electron and be deflected again, and again, and again, billions of times per second. Photons were effectively trapped. They could not travel any meaningful distance in a straight line. They were constantly bouncing around like balls in a cosmic pinball machine. This is called Thomson scattering, and it meant that the universe, despite being filled with radiation, was completely opaque. If you had eyes and could somehow exist in this environment, you would see nothing but a blinding, uniform glow in every direction. You could not see your hand in front of your face because the photons from your hand would be scattered in random directions before they could reach your eyes. The entire universe was a brilliant, glowing, impenetrable wall of light. This era lasted for 380,000 years. 380,000 years of opacity. 380,000 years during which the universe was essentially invisible to itself. No information could be transmitted by light over any meaningful distance. And this, by the way, is why I said earlier that the CMB is the oldest light that can ever be observed. Not because there was no light before, there was plenty, but because that light was trapped, scattered, randomized, and carries no useful information about the state of the universe at that time. The CMB is the first light that was actually free to travel, the first light that carries a coherent message. And then, roughly 380,000 years after the Big Bang, something remarkable happened. Something quiet, undramatic, but cosmically momentous. The universe cooled to a temperature of about 3,000 Kelvin, roughly 5,000 degrees Fahrenheit. And at this temperature, a crucial threshold was crossed. Electrons finally had low enough energy that they could be captured by protons. The free electrons, which had been buzzing around and scattering every photon in sight, were grabbed by hydrogen and helium nuclei and locked into orbits around them, forming the first electrically neutral atoms. Physicists call this event recombination, which is actually a terrible name because it implies the electrons and protons had been combined before and were recombining, when in fact they had never been combined. They were coming together for the first time. But the name stuck, and so we call it recombination. And recombination changed everything. Because once the electrons were bound into atoms, they were no longer free to scatter photons. The photons, which had been trapped for hundreds of thousands of years, were suddenly free. Freed from their 380,000-year imprisonment, the photons streamed outward in all directions. The fog cleared, the universe became transparent, and the light that was released at that moment, that specific moment, when the universe transitioned from opaque to transparent, that light is the cosmic microwave background. Every single photon in the CMB was released at roughly the same time, from roughly the same conditions. And those photons have been traveling through space ever since, for 13.8 billion years, crossing unimaginable distances until today. Right now, some of them are reaching your eyes, your skin, and the sensitive instruments we have built to detect them. The CMB is a snapshot, a photograph, the first and oldest photograph of the universe, taken not by a camera, but by the universe itself at the moment it first became transparent. It is a baby picture of the cosmos, captured when the universe was a mere infant, just 380,000 years old. And like any baby picture, it shows us what the universe looked like at that tender age. It shows us the features and characteristics that would later grow and develop into the magnificent cosmic structures we see today. Galaxies, clusters, superclusters, the great cosmic web, all of it was foreshadowed, all of it was seeded in the patterns captured by this ancient light. Before we go further into what the CMB shows us, I want to tell you one of the most incredible stories in the history of science. The story of how the CMB was predicted, ignored, and then accidentally discovered. Because this story is not just scientifically important, it is a deeply human story, full of brilliance, irony, bad luck, good luck, and pigeons. Yes, pigeons. Now, before I get into that incredible discovery story, I want to know something. Where are you watching this video from right now? Seriously, drop your country and your city in the comments below. It genuinely amazes me every single time that people from all around the world, from completely different countries, different cultures, different languages, come together in one place to learn about the universe. There is something beautiful about that. And if you are enjoying this journey so far, if you can feel that sense of wonder building, do me a favor and hit that like button right now. It takes 1 second and it makes a huge difference in helping this video reach more curious minds like yours. And trust me, what is coming next in this story is even more incredible than what you have heard so far. So let us keep going. The story begins in the 1940s with a man named George Gamow. Gamow was a Ukrainian-born American physicist, and he was, by all accounts, one of the most creative, playful, and unconventional scientists of his era. He was brilliant, but he was also a showman, a joker, and a man who loved intellectual puzzles of every kind. He wrote popular science books with titles like 1, 2, 3 Infinity and Mr. Tompkins in Wonderland. He was known for his wit, his love of practical jokes, and his ability to take extremely complex physics and make it accessible and entertaining. He was also, crucially, one of the first scientists to seriously think about the physics of the early universe. Gamow reasoned as follows. If the Big Bang happened, if the universe really did start in an incredibly hot, dense state, then the early universe must have been filled with intense radiation. As the universe expanded and cooled, that radiation would have cooled along with it. And it should still be there today, filling all of space, but greatly cooled down from its original searing temperatures to something just barely above absolute zero. In other words, the Big Bang should have left behind an afterglow, a faint, cold remnant of its initial heat, detectable as a faint radiation permeating all of space. Working with his students Ralph Alpher and Robert Herman, Gamow developed this idea into a concrete prediction. In the late 1940s, Alpher and Herman calculated that this residual radiation should exist today at a temperature of roughly 5 Kelvin, that is 5 degrees above absolute zero, the lowest possible temperature. This is remarkably close to the actual value, which we now know is about 2.7 Kelvin. Now, there is a wonderful side story here that I have to tell you because it is so perfectly George Gamow. When Alpher wrote his doctoral thesis laying out this theory, Gamow decided that the author list should read Alpha, Beta, Gamow, Alpha, Beta, Gamma, the first 3 letters of the Greek alphabet. The problem was that Hans Bethe, a famous physicist, had nothing to do with the paper. Gamow added his name purely for the joke. Reportedly, Bethe was amused and agreed to have his name on the paper, and Alpher was annoyed because people assumed Bethe had done significant work on it, diluting Alpher's contribution. This is the famous Alpha Beta Gamma paper, and it remains one of the most delightfully named scientific publications in history. But here is where the story takes a tragic turn. Despite the brilliance of this prediction, despite the fact that Gamow, Alpher, and Herman had essentially told the world exactly what to look for and approximately where to find it, the scientific community largely ignored them. The prediction was published. It was out there in the literature. But almost nobody paid attention. Why? Several reasons. First, the dominant cosmological model at the time was not the Big Bang theory, but something called the steady-state theory. This was championed by Fred Hoyle, Herman Bondi, and Thomas Gold, and it proposed that the universe had no beginning and no end. According to the steady-state theory, the universe has always existed, and always will exist, in roughly its current form. New matter is continuously created to fill in the gaps as the universe expands, so the overall density stays the same. The universe, in this view, is eternal and unchanging in its large-scale properties. The steady-state theory was elegant, philosophically appealing, and had the support of some very influential physicists, particularly Fred Hoyle, who was one of the most prominent astrophysicists in the world. And here, another irony. The very term Big Bang was coined by Fred Hoyle himself during a BBC radio broadcast in 1949. And he did not mean it as a compliment, he was mocking the idea. He thought the notion that the universe had a specific beginning was absurd, almost religious in its implications. So he dismissively called it the Big Bang, and the name, much to his eternal annoyance, stuck. The greatest and most widely used term in cosmology was invented as an insult by someone who thought the entire concept was nonsense. The second reason Gamow's prediction was ignored was more practical. The technology needed to detect such faint microwave radiation was not obviously available. It was unclear whether any existing instrument could actually measure a signal as faint as a few degrees above absolute zero, uniformly filling all of space. The prediction seemed interesting in theory, but impossible to test in practice. So it gathered dust. Gamow, Alpher, and Herman had given the world one of the most important predictions in the history of cosmology, and the world shrugged. Fast forward to the early 1960s. At Princeton University, a physicist named Robert Dicke and his young colleague Jim Peebles independently arrived at the same conclusion that Gamow's group had reached nearly 2 decades earlier. They realized that the Big Bang should have left behind a residual radiation, and they set about calculating its expected temperature and properties. Moreover, they decided to actually build a detector to look for it. They assembled a team, including David Wilkinson and Peter Roll, and began constructing a radiometer, a sensitive instrument designed to detect faint microwave radiation from the sky. They were on the verge of making one of the greatest discoveries in the history of science. But as you will see, fate had other plans. About 30 miles away from Princeton, at the Bell Telephone Laboratories in Holmdel, New Jersey, 2 radio astronomers named Arno Penzias and Robert Wilson were working on a completely different project. They were using a large horn-shaped antenna that had originally been built for satellite communication, specifically for the Echo Balloon satellite project. The antenna was no longer needed for its original purpose, and Penzias and Wilson wanted to repurpose it for radio astronomy. They were interested in measuring the radio emission from our own Milky Way galaxy at microwave wavelengths. To do this accurately, they needed to calibrate their instrument extremely precisely. They needed to account for every possible source of noise, every signal that was not from the Milky Way, so they could subtract it and isolate the galactic signal they were interested in. And this is where the trouble started. When they pointed their antenna at the sky and measured the incoming microwave signal, they found an excess, a persistent, low-level, mysterious signal that they could not explain? It was faint, barely 3.5 Kelvin, but it was there. It was everywhere. It did not matter where they pointed the antenna, north, south, east, west, up, down, day or night, summer or winter. The signal was the same. It was isotropic, meaning it came from all directions equally. It had no source. It seemed to be coming from everywhere at once, which made no sense to them. A signal that comes from everywhere and has no identifiable source? That is not how radio sources work. Radio sources are point-like. They come from specific objects, specific locations in the sky. Stars, galaxies, nebulae. Not from everywhere simultaneously. Penzias and Wilson were convinced it was an error, some kind of instrumental artifact, some source of noise they had not accounted for. So they began a systematic, painstaking, months-long campaign to eliminate every possible source of contamination. They checked their electronics. They rewired connections. They recalibrated their instruments. They tested for radio interference from nearby cities. They accounted for the signal from the atmosphere. They checked for radiation from nuclear weapons tests, which had been conducted in the atmosphere in the years before and could potentially contribute a faint signal. They checked everything, and then they found the pigeons. A pair of pigeons had made a nest inside the horn of the antenna. They were roosting there, and they had covered the interior surfaces with what Penzias later diplomatically described as a white dielectric material. Bird droppings. Pigeon poop. Penzias and Wilson thought they had found the culprit. The pigeon droppings might be warm enough to radiate at microwave frequencies and contaminate their measurements. So they carefully removed the pigeons. They trapped them, drove them to a location far away, and released them. Then they meticulously cleaned out the antenna, removing every trace of the white dielectric material. But the pigeons, being pigeons, flew right back. Pigeons have an excellent homing instinct. So Penzias and Wilson had to deal with the pigeons again. Eventually, the pigeons were permanently removed. I will leave the exact fate of the pigeons to your imagination. They cleaned the antenna thoroughly. They recalibrated everything. They measured again, and the signal was still there, exactly the same. The persistent, uniform, all-sky microwave signal had not budged by even a fraction. It was not the pigeons. It was not the electronics. It was not interference. It was real. Something was genuinely filling the sky with a faint microwave glow at a temperature of about 3.5 Kelvin. And Penzias and Wilson had no idea what it was. They wrote it up as an unexplained excess antenna temperature, and they were baffled. Now here is where the story reaches its climax, and it involves one of those coincidences that make the history of science read like a novel. Penzias happened to mention his mystery signal to a colleague, Bernard Burke, who had recently heard about the theoretical work being done by Dickey and Peebles at Princeton. Burke told Penzias, "You should call Bob Dicke at Princeton. He is working on something that might explain your signal." So Penzias called Dicke. And when Dicke received the call, when he heard Penzias describe the uniform, isotropic, 3.5 Kelvin microwave signal that filled the entire sky, he immediately knew what it was. He hung up the phone, turned to his colleagues, and said what has become one of the most famous sentences in the history of physics. He said, "Boys, we have been scooped." They had been scooped indeed. While Dicke's team at Princeton was still building their detector, still preparing to search for the cosmic background radiation, Penzias and Wilson had stumbled upon it by pure accident, using an instrument that was not even designed for the purpose. In 1965, two landmark papers were published back-to-back in the Astrophysical Journal. One, by Penzias and Wilson, described the observation, the unexplained excess antenna temperature that they had detected. The other, by Dicke, Peebles, Roll, and Wilkinson, provided the theoretical interpretation, explaining that the signal was the predicted remnant radiation from the Big Bang, the cosmic microwave background. Together, these two papers changed cosmology forever. The impact was seismic. The discovery of the CMB was the nail in the coffin of the steady-state theory. If the universe had always existed in its current form, there was no reason for a uniform microwave background to exist. But if the universe had started in a hot, dense state and expanded and cooled over billions of years, then this background radiation was exactly what you would expect. The CMB was the smoking gun for the Big Bang. The debate that had raged for decades between Big Bang and steady state was effectively over. Some steady-state proponents held out for a while, proposing alternative explanations. But the evidence was overwhelming. The universe had a beginning. The Big Bang was real, and the proof was glowing faintly in every direction. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for their discovery. It was richly deserved. But the history of science is not always fair, and several injustices cling to this story. George Gamow, who first predicted the existence of the CMB, had died in 1968, and Nobel Prizes are not awarded posthumously. Ralph Alpher and Robert Herman, who made the first quantitative predictions of the CMB temperature, never received the Nobel Prize. Alpher in particular felt deeply bitter about this until his death in 2007. And Robert Dicke, who independently predicted the CMB and would have discovered it himself if he had been just a few months faster, also did not receive the Nobel. Jim Peebles, however, the youngest member of Dicke's Princeton team, continued to make foundational contributions to cosmology for the next half-century, and was finally awarded the Nobel Prize in Physics in 2019, more than 50 years after the events I have just described. Science, like life, is often not fair. Credit does not always go to those who most deserve it. Timing matters, luck matters, and sometimes the pigeon poop matters. But regardless of who gets the credit, the discovery itself stands as one of the most important observations in the entire history of human science. The CMB confirmed the Big Bang theory. It gave us direct observational access to the early universe. It opened a window in time that allowed us to see back 13.8 billion years to an era long before the first stars, the first galaxies, or anything else that we normally think of as the universe. It transformed cosmology from a largely speculative, philosophical discipline into a precision science. And as we will see, the CMB continues to yield new insights and new mysteries to this day. Now let us talk about what the CMB actually is in physical terms. What are we really detecting? What kind of signal is it, and what does it tell us? The CMB is thermal radiation. Specifically, it is blackbody radiation. Now, I need to explain what this means because it is fundamental to understanding why the CMB is so important and so informative. Every hot object emits radiation. This is a basic fact of physics. The hotter an object is, the more radiation it emits, and the higher the energy, the shorter the wavelength of that radiation. A lump of iron at room temperature emits infrared radiation, which you cannot see but can feel as heat. Heat that same iron to a few hundred degrees Celsius, and it begins to glow a dull red. Heat it more, and it glows orange, then yellow, then white. This is because as the temperature rises, the peak of the emitted radiation shifts to shorter wavelengths, from infrared to red to yellow to blue. This relationship between an object's temperature and the spectrum of radiation it emits is described by a concept called blackbody radiation. A blackbody is an idealized object that absorbs all incoming radiation and re-emits it in a spectrum that depends only on its temperature. The mathematical formula for a blackbody spectrum was derived by Max Planck in 1900, and it was actually this derivation that launched the quantum revolution in physics. So blackbody radiation is not just relevant to the CMB, it is central to the history of all modern physics. The CMB has a blackbody spectrum, and not just any blackbody spectrum. The most perfect blackbody spectrum ever measured by anything, anywhere, in the entire history of science. Let me repeat that, because I want it to sink in. The cosmic microwave background has the most perfect blackbody spectrum ever measured in nature, more perfect than any laboratory blackbody, more perfect than any object on Earth, more perfect than any star. When the COBE satellite, the first satellite dedicated to studying the CMB, measured its spectrum in 1990 using an instrument called FIRAS, the Far Infrared Absolute Spectrophotometer, the results were staggering. The measured spectrum fit the theoretical blackbody curve so perfectly that the error bars, the uncertainties in the measurement, were smaller than the thickness of the line drawn on the graph to represent the theoretical curve. You could not distinguish the data from the theory. They were identical to within the precision of the measurement. When John Mather presented this result at the American Astronomical Society meeting in January 1990, the audience of professional astronomers and physicists gave him a standing ovation. Physicists do not normally give standing ovations. This was exceptional. They were looking at data so clean, so perfect, so beautiful, that it elicited spontaneous applause from the most skeptical, hard-nosed scientists in the world. John Mather later shared the 2006 Nobel Prize in Physics for this measurement. The temperature of this perfect blackbody is 2.7255 Kelvin. That is about negative 270.4 degrees Celsius, or negative 454.8 degrees Fahrenheit, just 2.7 degrees above absolute zero, the coldest possible temperature. But remember, this radiation did not start out this cold. When it was first released, at the moment of recombination 380,000 years after the Big Bang, its temperature was about 3,000 Kelvin. That is roughly the temperature of a cool star's surface. At that temperature, the radiation was in the visible spectrum, specifically a warm orange-red glow. If you had been there, the entire universe would have been glowing with a warm orange light, everywhere, in every direction. The sky would not have been dark. It would have been a uniform, warm glow. So how did this warm, visible light become the cold, invisible microwave radiation we detect today? The answer is one word: expansion. As the universe expanded, space itself stretched. And as space stretched, it stretched the wavelength of every photon traveling through it. This is called cosmological redshift. It is similar to the Doppler effect, where the sound of a siren changes pitch as the siren moves toward or away from you. But it is not quite the same. Cosmological redshift is not caused by the motion of a source through space. It is caused by the expansion of space itself. As the photon travels through expanding space, the very fabric of the universe stretches the photon's wavelength. Longer wavelength means lower energy, which means lower temperature. Over 13.8 billion years of cosmic expansion, the wavelength of the CMB photons has been stretched by a factor of roughly 1,100. They started as visible light and have been stretched all the way to microwave radiation. And this factor of 1,100 tells us something profound. It tells us that the universe has expanded by a factor of roughly 1,100 since the CMB was released. The universe today is about 1,100 times larger than it was 380,000 years after the Big Bang. Think of it this way. Imagine drawing a wave on a rubber band, a nice short wave. Now stretch the rubber band. As you pull the ends apart, the wave gets longer. Its wavelength increases. The CMB photons are like waves drawn on the rubber band of space. As space has expanded, their wavelengths have stretched. What started as orange visible light has been stretched into invisible microwave radiation, and we can detect it. Let me talk about where the CMB comes from spatially. When we observe the CMB, we are looking at what cosmologists call the surface of last scattering. This is not a physical surface. There is no wall out there in space from which the CMB emanates. Rather, it is a moment in time that we perceive as a surface. Let me explain. Because light travels at a finite speed, when we look at distant objects, we are looking back in time. When you look at the sun, you are seeing it as it was 8 minutes ago, because sunlight takes 8 minutes to reach Earth. When you look at the nearest star, Alpha Centauri, you are seeing it as it was about 4 years ago. When you look at a galaxy a billion light years away, you are seeing it as it was a billion years ago. The farther you look, the further back in time you see. Now extend this principle to the CMB. The CMB photons have been traveling for 13.8 billion years. So when we detect them, we are looking back 13.8 billion years to a time when the universe was only 380,000 years old. And we see this radiation coming from every direction. So it appears to come from a sphere surrounding us. A sphere at a distance corresponding to 13.8 billion years of light travel time. This sphere is the surface of last scattering. But here is the crucial point. Beyond this sphere at earlier times, the universe was opaque. Photons could not travel freely, so we cannot see beyond the surface of last scattering using electromagnetic radiation, meaning any form of light. The CMB is the ultimate curtain. It is the farthest back we can ever look using light. Everything beyond it, everything that happened in the first 380,000 years, is hidden behind this wall of glowing plasma. It is like standing in the middle of a thick fog. You can see to the edge of the fog, where it thins out and becomes transparent. But beyond that, everything is obscured. The surface of last scattering is the cosmic fog bank. We can see to its edge, but no further, at least not with light. We will come back to this point later, because there are other messengers, not light, but neutrinos and gravitational waves that might someday allow us to peer behind the curtain and see even further back. Now, one of the first and most striking things about the CMB is its uniformity. It has a temperature of 2.7255 Kelvin, and this temperature is the same in every direction to an astonishing degree of precision. Wherever you point your antenna, the temperature is 2.7255 Kelvin, north, south, east, west, toward the center of the Milky Way, away from it, toward the great voids of deep space, toward the densest galaxy clusters. It does not matter. The CMB temperature is the same. This uniformity, by the way, was actually a major problem for cosmology before inflation was proposed. It is called the horizon problem. Regions of the sky that appear to be far apart, on opposite sides of the sky, for instance, were never in causal contact with each other, meaning that no signal, not even light, could have traveled from one to the other in the time available. So how could they possibly be at the same temperature? If I put 2 cups of coffee in separate rooms that have never been connected, I would not expect them to cool to exactly the same temperature at exactly the same time. There must have been some kind of communication, some process that equalized their temperatures. And the answer, as I mentioned earlier, is inflation. During inflation, the entire observable universe was once an incredibly tiny region, small enough that all parts of it were in contact and had equilibrated to the same temperature. Then inflation blew that tiny region up to cosmic scales, preserving the temperature uniformity. So the reason the CMB is the same temperature in every direction is that all of the observable universe was once in thermal equilibrium, and inflation preserved that equilibrium across the now vast distances. But within this astonishing uniformity, there are tiny variations. Fluctuations so small that they were not detected until more than 2 decades after the CMB itself was discovered. These fluctuations are about 1 part in 100,000. That means if the average temperature is 2.7255 Kelvin, the variations are on the order of plus or minus a few tens of millionths of a degree. To give you a sense of how tiny this is, imagine that the average temperature of the CMB is represented by a skyscraper, say, a building 300 meters tall. The temperature fluctuations in the CMB would be like placing a single sheet of paper on top of that skyscraper. That is the scale of variation we are talking about. Barely detectable, almost imperceptible. And yet, these minuscule variations are, without exaggeration, the most important features in the entire CMB, because those tiny temperature fluctuations are the seeds of all structure in the universe. They are the reason anything exists. They are the reason you exist. Without them, the universe would be a perfectly uniform, featureless void forever. We are about to get into something truly mind-blowing now, something that connects quantum mechanics to the formation of galaxies, that links the smallest scales in physics to the largest scales in the cosmos. We are going to talk about how those tiny temperature differences, those millionths of a degree, became everything. But before we do that, if you have not subscribed to this channel yet, now is the time. I am not asking you to do something for me. I am asking you to do something for yourself. Because we go deep on topics like this regularly, and every single time, we find something that changes the way you think about the universe. So hit subscribe, turn on that notification bell, and do not miss what is coming next. Because the next part of this story, I promise you, is going to change the way you think about your own existence. Let us talk about that famous CMB map. You have probably seen it. It is an oval-shaped projection, like a Mercator map of the Earth, but for the entire sky. And it is covered in splotches of blue and red and yellow and orange. It looks almost like a heat map. And in a sense it is. The colors represent temperature variations. Red and yellow spots are regions that are slightly warmer than average by a few millionths of a degree. Blue and green spots are regions that are slightly cooler than average, also by a few millionths of a degree. And these color variations correspond to density variations in the early universe. Slightly warmer spots were slightly denser regions of the primordial plasma. Slightly cooler spots were slightly less dense regions. Why the correlation between temperature and density? Because in a denser region, the plasma is more compressed, and compression heats things up. Just like a bicycle pump gets warm when you compress air. The denser the region, the hotter it was, the warmer its CMB photons are today. And where did these density variations come from? This is where we return to inflation and one of the most profound connections in all of physics. During inflation, the universe was subject to quantum fluctuations. Now, quantum fluctuations are not exotic or unusual. They are a fundamental, inherent, unavoidable feature of quantum mechanics. According to the Heisenberg uncertainty principle, even empty space, a perfect vacuum, is not truly empty. It is seething with activity, with particles and antiparticles popping in and out of existence, with fields flickering up and down. These fluctuations are normally incredibly tiny, confined to subatomic scales. They are the quantum fuzz of reality, usually invisible and irrelevant to the macroscopic world. But during inflation, something extraordinary happened. The exponential expansion of space grabbed these minuscule quantum fluctuations and stretched them to enormous scales. What was once a fluctuation the size of an atom was blown up to a fluctuation spanning millions of light years. Quantum randomness, the fundamental graininess of reality at the smallest scales, was projected onto the cosmic canvas. The microscopic became the macroscopic. The random became the structural. When inflation ended and the universe transitioned to its normal, slower expansion, these inflated quantum fluctuations became real. Physical variations in the density of the primordial plasma. Some regions were slightly denser, some were slightly less dense. And these density variations, these seeds planted by quantum randomness and inflated to cosmic scales, are exactly what we see in the CMB map. The splotches of red and blue that cover the famous oval image are ultimately the direct descendants of quantum fluctuations from the first trillionth of a trillionth of a trillionth of a second of the universe. You're looking at quantum mechanics writ large across the sky. If that does not take your breath away, if that does not fill you with a sense of awe and wonder, then I do not know what will. The patterns on the CMB are the quantum fingerprint of creation, but the story of these density fluctuations between their creation during inflation and their preservation in the CMB is even more rich and fascinating than I have conveyed so far. Because during those first 380,000 years, while the universe was still a hot plasma, something amazing was happening. The plasma was ringing, like a bell, like a drum. The universe was filled with sound, not sound that you could hear with your ears, of course. Sound is a pressure wave, and the early universe was one giant connected fluid of plasma. And in that fluid, the density fluctuations from inflation were driving acoustic oscillations, genuine sound waves that propagated through the primordial plasma at about half the speed of light. Here is how it worked. In a region that was slightly denser than average, gravity was pulling the plasma inward, trying to compress it further. But as the plasma compressed, its pressure increased, and the radiation within it pushed back outward. This created an oscillation. Gravity pulled in, pressure pushed out. Gravity pulled in, pressure pushed out. Like a spring, like a vibrating drumhead. These were literal sound waves, pressure waves oscillating back and forth through the cosmic plasma. These oscillations are called baryon acoustic oscillations, and they are one of the most beautiful phenomena in all of cosmology. The early universe was singing. It had a fundamental frequency, a cosmic bass note, determined by the size of the universe and the speed of sound in the plasma. And it had higher harmonics, overtones, just like a musical instrument. The universe was not just producing one note, it was producing a chord, a rich spectrum of tones. And when recombination happened, when the universe transitioned from opaque plasma to transparent gas, these oscillations were frozen in place. The music stopped. The sound waves were caught in mid-vibration, locked into the pattern of density variations that existed at that exact moment. And that frozen pattern is what we see in the CMB. The splotches on the CMB map are not random. They have characteristic sizes that correspond to the wavelengths of these acoustic oscillations. The biggest splotches correspond to the fundamental frequency. Smaller splotches correspond to the harmonics. The CMB is a snapshot of the universe's primordial music. Frozen at the moment the cosmic symphony was silenced. Now, to extract the detailed information encoded in these oscillations, cosmologists use a mathematical tool called the angular power spectrum. This is, in my opinion, the single most important graph in all of cosmology. Let me explain what it is and what it tells us. The angular power spectrum is a graph that shows how much temperature variation there is in the CMB at different angular scales. On the horizontal axis, you have the angular scale, from large-scale features spanning many degrees on the sky to small-scale features spanning fractions of a degree. On the vertical axis, you have the amount of temperature variation at each scale. And what the graph shows is not a smooth curve, but a series of peaks and valleys. A characteristic wavy pattern that looks almost like a mountain range with several distinct summits. These peaks are the acoustic peaks, and they correspond to the harmonics of the cosmic sound waves I just described. The first peak, the tallest and most prominent, corresponds to regions that had completed exactly one full compression by the time of recombination. These regions were at maximum density, maximum temperature, and so they produced the strongest temperature variation. The position of this first peak, the angular scale at which it appears, tells us something breathtaking. It tells us the geometry of the universe. You see, the angular scale of the first peak depends on the actual physical size of these compressed regions, which we can calculate from the physics of the plasma, and on how large they appear to us, which depends on how light has traveled through the universe to reach us. And how light travels through the universe depends on the geometry of space. If space is positively curved like the surface of a sphere, then light converges and things appear larger. The first peak would be at a larger angular scale. If space is negatively curved like a saddle, then light diverges and things appear smaller. The first peak would be at a smaller angular scale. And if space is flat like a perfectly flat tabletop extending in all directions, then the first peak appears at a very specific angular scale, roughly 1 degree on the sky. And that is exactly where we observe it. The first peak is at almost exactly 1 degree. This means the universe is flat. Flat in the geometric sense. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees. The rules of Euclidean geometry that you learned in school apply to the universe at the largest possible scales. And the precision of this measurement is remarkable. The universe is flat to within about 0.4%. Not approximately flat. Not sort of flat. Flat to 4 parts in 1,000. This is one of the most precise measurements in all of cosmology, and it comes directly from the position of the first peak in the CMB power spectrum. The second peak tells us something different. Its height, relative to the first peak, is sensitive to the amount of ordinary matter in the universe. By ordinary matter, I mean baryonic matter. The stuff made of protons, neutrons, and electrons. The stuff that makes up atoms, molecules, stars, planets, and you. The physics is subtle, but the idea is straightforward. The amount of baryonic matter in the plasma affects how the acoustic oscillations behave. More baryonic matter means more inertia in the oscillation, which changes the relative heights of the even and odd peaks. By carefully measuring the second peak, cosmologists have determined that ordinary baryonic matter makes up about 4.9% of the total energy content of the universe, just 5%. Everything you have ever seen, touched, detected, or interacted with, every star, every galaxy, every planet, every person, every atom, makes up less than 5% of the universe. The third peak tells us about something else entirely. Its height is sensitive to the amount of dark matter. Dark matter is a form of matter that does not interact with light. It does not emit light, absorb light, or scatter light. It is completely invisible to every telescope ever built, at every wavelength, from radio to gamma rays. But it has mass, and therefore it has gravity. And its gravitational effects are detectable. Dark matter does not participate in the acoustic oscillations because it does not interact with photons. While ordinary matter was oscillating back and forth, pushed by radiation pressure and pulled by gravity, dark matter was just sitting there, pulled only by gravity, slowly accumulating in the denser regions. This means dark matter affects the CMB differently from ordinary matter, and its fingerprint is most clearly visible in the third acoustic peak. By measuring this peak, cosmologists have determined that dark matter makes up about 26.8% of the total energy content of the universe. More than 5 times as much as ordinary matter. There is 5 times more invisible stuff in the universe than visible stuff. And we still do not know what dark matter is. We know it exists. The evidence from the CMB alone is overwhelming, and it is corroborated by galaxy rotation curves, gravitational lensing, the formation of large-scale structure, and many other observations. But its fundamental nature, whether it is a new particle, a new force, or something else entirely, remains one of the greatest unsolved mysteries in physics. And then there is the overall shape of the power spectrum, the way the peaks relate to each other and to the background, which tells us about the remaining 68.3% of the universe's energy content. This is dark energy. Dark energy is even more mysterious than dark matter. It is a form of energy that permeates all of space and is causing the expansion of the universe to accelerate, not just to continue, but to speed up. Galaxies are flying apart from each other faster and faster, and we have almost no understanding of what dark energy actually is. The simplest explanation is that it is the cosmological constant, a term that Einstein originally introduced into his equations of general relativity and then later called his greatest blunder. The cosmological constant represents a fixed energy density of the vacuum of space itself, a kind of inherent energy that empty space possesses simply by virtue of existing. And remarkably, the CMB data are consistent with dark energy being exactly a cosmological constant. But why it has the value it has, why it exists at all, and whether it might change over time, these are questions we cannot yet answer. So from this one image, this one measurement, this ancient light, we have extracted the following information. The universe is flat. The universe is 13.8 billion years old. Ordinary matter makes up about 5% of the universe. Dark matter makes up about 27%. Dark energy makes up about 68%. 95% of the universe is made of stuff we cannot see, cannot touch, and do not understand. All of this from one source of light, one ancient glow. The CMB is not just a baby picture of the universe, it is the Rosetta Stone of cosmology. But the CMB does not just tell us about the composition of the universe in terms of these big categories. It goes much deeper. Let me take you through how those tiny fluctuations, those seeds of quantum randomness, actually grew into the galaxies and cosmic structures we see today. Because this is the story of our own origin. After recombination, after the CMB was released and the universe became transparent, the density fluctuations were frozen into the distribution of matter. Slightly denser regions contained slightly more matter. And because they had more matter, they had slightly stronger gravitational pull. This extra gravity attracted more matter from the surrounding regions, making these dense regions even denser, which gave them even more gravity, which attracted even more matter. This is a process called gravitational instability, and it is a positive feedback loop. The rich get richer. Dense regions become denser. Underdense regions become emptier. Over millions and hundreds of millions of years, this gravitational amplification turned tiny, barely perceptible variations in density into genuine structures, gas clouds, dark matter halos, proto-galaxies. But here is the thing, and this is crucial. Without dark matter, this process would not have worked, or at least not in the time available. The density fluctuations in ordinary matter alone were too small. The temperature variations in the CMB, 1 part in 100,000, correspond to density variations that are also about 1 part in 100,000. And the gravitational pull from such tiny variations in ordinary matter alone would not have been strong enough to form galaxies by the time we observe them, which is as early as a few 100 million years after the Big Bang. The ordinary matter needed help, and dark matter provided that help. Remember, dark matter does not interact with photons. It was not affected by the radiation pressure that was pushing ordinary matter around during the acoustic oscillations. So while ordinary matter was sloshing back and forth, dark matter was quietly accumulating in the denser regions, undisturbed by radiation pressure. By the time of recombination, dark matter had already begun to form gravitational wells, concentrated regions of dark matter that were denser than their surroundings. And after recombination, when ordinary matter was freed from its coupling to radiation, It fell into these dark matter wells. The dark matter had prepared the gravitational scaffolding, and ordinary matter simply fell into the framework. This is how galaxies formed, not from ordinary matter alone, but from ordinary matter falling into pre-existing dark matter structures. The Milky Way, our home galaxy, is sitting inside an enormous halo of dark matter that extends far beyond the visible edges of the galaxy. We are embedded in dark matter. We live inside it, and without it, we would not exist. Over hundreds of millions and billions of years, the gravitational amplification of these initial density fluctuations produced the cosmic web, the large-scale structure of the universe. If you could zoom out and see the universe from a great distance, you would see an intricate, three-dimensional network of filaments and nodes, like a cosmic spider's web. The filaments are vast rivers of dark matter and galaxies, stretching across hundreds of millions of light years. The nodes, where filaments intersect, are massive galaxy clusters containing hundreds or thousands of galaxies. And between the filaments are great voids, enormous empty regions where there is almost no matter at all. Some of these voids are hundreds of millions of light years across. This cosmic web was not designed. It was not planned. It emerged spontaneously from the gravitational amplification of tiny quantum fluctuations that were stretched to cosmic scales during inflation, imprinted on the CMB, and then grew under the influence of gravity for 13.8 billion years. The pattern of galaxies in the sky today is a direct, evolved, amplified version of the pattern of temperature fluctuations in the CMB. The splotches on that oval map literally became the galaxies in the universe, and this means something personal, something existential. The Milky Way galaxy exists because of a particular temperature fluctuation in the CMB. A specific spot, slightly warmer than its surroundings by a few millionths of a degree, was the seed of our galaxy. It was a slightly denser region of primordial plasma, which became a slightly denser region of dark matter, which attracted ordinary matter, which formed a proto-galaxy, which evolved over billions of years into the majestic spiral galaxy we call home. And within that galaxy, the sun formed from a cloud of gas and dust, and around the sun, the earth formed, and on the earth, life emerged, and that life evolved over billions of years into you, sitting there, watching this video, learning about the very process that created you. You are the universe becoming aware of itself. You are the CMB's creation, looking back at its own origin. If that thought does not move you, I think nothing will. Now, I want to take you through the missions that mapped the CMB, because the story of how we went from Penzias and Wilson's crude first detection to the exquisite maps we have today is a story of technological triumph and scientific perseverance. The first dedicated satellite mission to study the CMB was COBE, the Cosmic Background Explorer. COBE was a NASA satellite launched in November 1989, and it carried two instruments that are relevant to our story. The first was FIRAS, the Far-Infrared Absolute Spectrophotometer, which I mentioned earlier. FIRAS measured the spectrum of the CMB and confirmed that it is a perfect blackbody at 2.725 Kelvin. That measurement, as I described, earned a standing ovation from the scientific community. The second instrument was DMR, the Differential Microwave Radiometer, and it was designed to look for the temperature fluctuations, the anisotropies, in the CMB. Remember, for more than 2 decades after Penzias and Wilson's discovery, the CMB appeared to be perfectly uniform. No fluctuations had been detected, and this was actually becoming a serious problem for cosmology. Because if the CMB were truly perfectly uniform, with no fluctuations at all, then there would be no seeds for gravitational instability, and the formation of galaxies and large-scale structure could not be explained. The fluctuations had to be there, but they were so tiny that no instrument had been sensitive enough to detect them. COBE's DMR instrument changed that. In 1992, George Smoot and the COBE team announced the first detection of CMB anisotropies. For the first time, we could see that the CMB was not perfectly uniform. There were variations, tiny, barely detectable, but real. The amplitude of the variations was about 1 part in 100,000, exactly as inflation predicted. The scientific community erupted. George Smoot, in a moment of poetic exuberance, described the CMB map as like seeing the face of God. Stephen Hawking called it the most important discovery of the century, if not of all time. That might have been a slight exaggeration, but the excitement was justified. COBE had given us the first glimpse of the seeds of cosmic structure, the quantum fluctuations that became galaxies. Smoot and John Mather shared the 2006 Nobel Prize in Physics for the COBE results. But COBE's map was very blurry. Its angular resolution was about 7 degrees, which means it could not see features smaller than about 7 degrees on the sky. For comparison, the full moon is about half a degree across. So COBE could only see features larger than about 14 full moons. The CMB map from COBE looked like a fuzzy, pixelated mess. You could see that fluctuations were there, but you could not make out their detailed structure. It was like looking at a baby picture through frosted glass. You could tell it was a baby, but you could not see its features clearly. To extract the detailed information I described earlier, the acoustic peaks, the composition of the universe, the geometry of space, we needed a much, much sharper image. That sharper image came from WMAP, the Wilkinson Microwave Anisotropy Probe. WMAP was a NASA satellite launched in June 2001, and it operated until 2010, collecting 9 years of data. The satellite was named after David Wilkinson, one of the members of Dick's original Princeton team, who worked tirelessly on CMB studies until his death in 2002. WMAP was placed at the second Lagrange point, L2, a gravitationally stable point about 1.5 million kilometers from Earth on the side opposite the Sun. This location is ideal for space observatories because it keeps the Earth, Sun, and Moon all on one side, making it easier to shield the telescope from their heat and radiation. The same location would later be used by the James Webb Space Telescope. WMAP had about 35 times better angular resolution than COBE, and its results were transformative. For the first time, the CMB map was sharp enough to clearly resolve the acoustic peaks in the power spectrum. And those peaks yielded a treasure trove of cosmological information. WMAP determined the age of the universe to be 13.77 billion years, with an uncertainty of only 60 million years. It confirmed that the universe is geometrically flat. It measured the composition of the universe: 4.6% ordinary matter, 24% dark matter, and 71.4% dark energy. It provided the first detailed evidence for cosmic inflation through the properties of the fluctuations. And it detected the polarization of the CMB, which opened up an entirely new dimension of information that we will discuss shortly. WMAP turned cosmology from a field where quantities were known to within factors of 2 or 3 into a precision science where quantities were known to within a few percent. It was a revolution. And then came Planck. The Planck satellite, operated by the European Space Agency, was launched in May 2009 and collected data until 2013. Planck was the Rolls-Royce of CMB satellites. It had even better angular resolution than WMAP, down to about 5 arc minutes, which is about 1/10 the angular size of the full moon. It observed in 9 frequency bands, compared to WMAP's 5, allowing much better separation of the CMB signal from foreground contamination like dust and gas in our own galaxy, and it measured both temperature and polarization with unprecedented sensitivity. The Planck results, released in a series of papers in 2013, 2015, and 2018, refined our knowledge of the universe to extraordinary precision. The age of the universe, 13.799 billion years, plus or minus 21 million years. That is a precision of 0.15%. We know the age of the universe to within 0.15%. Let that sink in. The Hubble constant, the rate at which the universe is expanding, 67.4 kilometers per second per megaparsec. With an uncertainty of less than 1%, the composition, 4.9% ordinary matter, 26.8% dark matter, 68.3% dark energy. The spectral index of the primordial fluctuations, 0.965, ruling out a perfectly scale invariant spectrum at very high significance, exactly as most inflationary models predict. If you compare the CMB maps from COBE, WMAP, and Planck side by side, the improvement is breathtaking. COBE's map is a fuzzy blob. WMAP's map is sharp and detailed. Planck's map is exquisitely crisp, revealing fine detail that was invisible before. Going from COBE to Planck was like going from a blurry ultrasound image to a high-definition photograph. Each mission built on the last, refining our understanding, answering old questions, and, as we will see, raising new ones. Can you believe this? From a single glow of ancient light, from photons that have been traveling for 13.8 billion years, we have figured out the age, shape, and composition of the entire universe. If this is blowing your mind as much as it blows mine every time I think about it, do me a favor. Drop a comment below. Tell me what is the most surprising thing you have learned so far. I genuinely read the comments, and I love hearing what resonates with you. And if you know someone who loves science, or someone who you think needs to hear this story, share this video with them. Let us spread this knowledge together, because this is not just my story or your story. This is the universe's story, and everyone deserves to hear it. Now let me go deeper into the specific revelations from the CMB, because each one is a story in itself. The flatness of the universe. I mentioned this earlier, but let me expand on it because it is genuinely one of the most remarkable findings in all of cosmology. When we say the universe is flat, we mean flat in the sense of geometry. There are 3 possible geometries for the universe, dictated by general relativity. If the total energy density of the universe is greater than a certain critical value, the universe has positive curvature. Space curves back on itself, like the surface of a sphere. In such a universe, parallel lines eventually converge, the angles of a triangle add up to more than 180 degrees, and the universe is finite in extent, you could, in principle, travel in one direction and eventually return to your starting point, like circumnavigating the Earth. If the total energy density is less than the critical value, the universe has negative curvature, like the surface of a saddle. In such a universe, parallel lines diverge. The angles of a triangle add up to less than 180 degrees, and the universe is infinite. And if the total energy density is exactly equal to the critical value, the universe is flat. Space obeys the rules of Euclidean geometry that you learned in school. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees, and the universe is probably infinite, though this is not absolutely certain. The CMB tells us that the universe is flat to within 0.4%. The total energy density is equal to the critical density to extraordinary precision. And this raises a profound question. Why? Why should the universe be so precisely flat? Because in an expanding universe, any deviation from perfect flatness grows over time. If the universe started out even slightly positively curved, that curvature would have amplified over 13.8 billion years, and we would observe significant positive curvature today. Similarly for negative curvature. For the universe to be as flat as we observe it today, it must have been incredibly, absurdly, almost impossibly flat at the very beginning. The initial curvature had to be tuned to at least one part in 10 to the 60. That is a 1 followed by 60 zeros. This seems like an extraordinary coincidence. Why would the initial conditions of the universe be so precisely fine-tuned? This is the flatness problem, and for decades, it was one of the great puzzles of cosmology. Inflation solves it. During inflation, the exponential expansion of space stretched any initial curvature to negligibility. Think of the surface of a balloon. If the balloon is small, you can easily see that it is curved. But if you inflate the balloon to an enormous size, the surface at any given point appears flat, because the curvature has been stretched to such a large scale that it is undetectable locally. Inflation inflated the balloon of the universe to such an enormous size that whatever initial curvature it had was stretched to flatness. The universe does not have to start flat. It just has to undergo inflation, and it will end up flat. This is one of the most elegant solutions in all of physics. The age of the universe, 13.799 billion years, plus or minus 21 million years. Let me put that precision in perspective. We know the age of the universe to within 0.15%. That means our uncertainty is only 21 million years out of 13.8 billion. By comparison, we often do not know the ages of geological formations on Earth to within that precision. We know the age of the universe better than we know the age of many rocks in our own backyard. How do we get this number from the CMB? It comes from the size of the sound horizon, the maximum distance that sound waves could have traveled through the primordial plasma between the Big Bang and recombination. This distance depends on the age of the universe at recombination and on the speed of sound in the plasma, both of which are determined by the composition of the universe, and the sound horizon determines the position of the first acoustic peak. So by measuring the first peak precisely and combining that with our knowledge of the physics of the plasma, we can calculate the age of the universe. and it cross-checks beautifully with other independent methods, such as the ages of the oldest stars in globular clusters, the expansion rate of the universe measured by other means, and the cooling rate of white dwarf stars. All these independent methods converge on the same answer, roughly 13.8 billion years, giving us tremendous confidence that this number is correct. Now let me talk about dark matter in a bit more detail, because the CMB provides some of the strongest evidence for its existence, and understanding this evidence is crucial for appreciating the full power of CMB science. Dark matter, as I mentioned, does not interact with light. It does not emit, absorb, or scatter electromagnetic radiation at any wavelength. So you cannot see it. You cannot photograph it. You cannot detect it directly with any telescope, but it has mass, and mass creates gravity, and gravity affects things that we can see. The evidence for dark matter comes from many sources, including the rotation curves of galaxies, the gravitational lensing of distant objects by foreground mass concentrations, the dynamics of galaxy clusters, and the large-scale structure of the universe. But the CMB provides evidence that is, in many ways, the most compelling and clean of all. Because the CMB comes from the early universe, before galaxies and clusters formed, before any complex astrophysics could muddy the waters. It is a pristine, direct probe of the fundamental parameters of the universe. And when you fit the CMB data with cosmological models, you find that the data absolutely require dark matter. Without dark matter, the power spectrum looks completely wrong. The relative heights of the peaks, the overall shape, the damping of the peaks at small scales, all of these features are exquisitely sensitive to the amount of dark matter. If you try to fit the data without dark matter with only ordinary matter, the fit is catastrophically bad. The data do not merely suggest dark matter, they demand it. And the amount they demand, about 27% of the universe's energy content, is completely consistent with other independent measurements. What is dark matter made of? We do not know. The leading candidates include weakly interacting massive particles, known as WMAPs, axions, sterile neutrinos, and various other hypothetical particles. Enormous experiments are underway around the world to detect dark matter particles directly, including deep underground detectors like Xenon, Lux Zeppelin, and Pandax. So far, none of these experiments have detected dark matter particles, which is itself an important result because it rules out many theoretical models and constrains the properties of whatever dark matter is. Some physicists have begun to wonder whether dark matter might not be a particle at all, but something more exotic, like primordial black holes formed in the early universe, or a modification of our theory of gravity. But the CMB data are very difficult to explain with modified gravity alone, and most cosmologists remain confident that dark matter is some form of matter made of particles that we have not yet discovered. Dark energy is even more mysterious. The CMB, combined with observations of distant supernovae and the large-scale distribution of galaxies, tells us that about 68% of the universe is dark energy. Dark energy is causing the expansion of the universe to accelerate. This was first discovered in 1998 through observations of Type 1a supernovae, and it was such a surprising result that it won the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. The CMB contributes to our understanding of dark energy in several ways. The overall geometry and expansion history of the universe affect the CMB, and fitting the CMB data with cosmological models constrains the amount and properties of dark energy. The CMB data are consistent with dark energy being the cosmological constant, meaning that its energy density is constant over time, and its equation of state parameter W equals exactly -1. But the CMB alone cannot determine W very precisely, which is why it is combined with other observations. The cosmological constant, if that is what dark energy is, raises perhaps the deepest puzzle in all of physics. According to quantum field theory, the vacuum of space should have an enormous energy density, arising from all the quantum fluctuations of all the fields in nature. When you calculate this vacuum energy using quantum field theory, you get a number that is roughly 10 to the power of 120 times larger than the observed value of the cosmological constant. That is not a typo. 10 to the 120. This is the largest discrepancy between a theoretical prediction and an observation in the entire history of science, and it has been called the worst prediction in the history of physics. Either there is some unknown mechanism that cancels almost all of the vacuum energy, leaving only a tiny residue, or our understanding of quantum field theory and gravity is fundamentally incomplete. Either way, it represents a profound gap in our understanding of nature, and the CMB, by precisely measuring the amount of dark energy and confirming that it behaves like a cosmological constant, has helped define the parameters of this crisis. Let me now talk about inflation in more detail, because the CMB is our best source of evidence for inflation. And inflation is one of the most important and beautiful ideas in all of cosmology. I introduced inflation earlier as a period of exponential expansion in the very first instance of the universe. Now let me describe how the CMB tests this idea. Inflation makes several specific, testable predictions about the properties of the CMB fluctuations, and the CMB data match these predictions remarkably well. First, inflation predicts that the fluctuations should be nearly scale invariant. This means that the amplitude of the fluctuations should be roughly the same on all scales. Big fluctuations and small fluctuations should have similar amplitudes. This is because during inflation, all scales were generated by the same physical mechanism. The stretching of quantum fluctuations and the exponential expansion treated all scales roughly equally. The CMB data confirm this. The fluctuations are indeed nearly scale invariant, but not perfectly. Inflation predicts a slight deviation from perfect scale invariance, a gentle tilt in the spectrum, because the inflating field was slowly rolling during inflation, and the conditions changed slightly over time. This tilt is characterized by a parameter called the spectral index, denoted N sub S. Perfect scale invariance corresponds to N sub S equals 1. Inflation typically predicts a value slightly less than 1, and the measured value from Planck is 0.965, in beautiful agreement with inflationary predictions and ruling out perfect scale invariance at very high statistical significance. This is a major triumph for the inflationary paradigm. Second, inflation predicts that the fluctuations should be Gaussian, meaning they should follow a bell-shaped statistical distribution. The probability of large fluctuations should be much smaller than the probability of small fluctuations, following the specific mathematical shape of a Gaussian distribution. This is because quantum fluctuations are inherently Gaussian. And the CMB data show that the fluctuations are indeed Gaussian to a very high degree of precision. Planck searched extensively for non-Gaussianity and found no significant detection, which is consistent with the simplest models of inflation. However, more complex models of inflation can produce detectable non-Gaussianity, and future experiments will search for these with even greater sensitivity. Third, inflation predicts that the fluctuations should be adiabatic, meaning that the same fluctuation affects all components of the universe, matter, radiation, dark matter, in the same way. This is in contrast to isocurvature fluctuations, where some components fluctuate while others do not. The CMB data strongly favor adiabatic fluctuations, again consistent with the predictions of the simplest inflationary models. Fourth, and this is the big one that has not yet been tested, inflation predicts the existence of primordial gravitational waves. I will devote an entire section to this later, because it is one of the most important frontiers in CMB science. So inflation makes at least 4 specific testable predictions, and the first 3 have been confirmed by the CMB data. This does not prove that inflation happened in the strict scientific sense, because other theories might also explain these features. But it makes inflation by far the most successful and well-supported theoretical framework for the origin of cosmic structure. No alternative theory comes close to matching the detailed agreement between inflationary predictions and CMB observations. Now, we come to what I consider the most exciting part of this entire story. The mysteries, the anomalies, the things that do not quite fit. Because science is not just about confirming theories, it is about confronting puzzles. And the CMB, for all its stunning agreement with our standard cosmological model, contains several features that are unexplained, puzzling, or outright disturbing. These anomalies might be statistical flukes. They might be the result of systematic errors or foreground contamination, or they might be the first hints of new physics beyond our current understanding, physics that could revolutionize our view of the universe. We do not know yet, and that uncertainty is what makes them so thrilling. Let me start with the biggest and most urgent anomaly, the one that has risen to the level of a genuine crisis in cosmology, the Hubble tension. The Hubble constant, denoted h0, is the rate at which the universe is expanding. It tells you how fast distant galaxies are receding from us, and it is one of the most fundamental numbers in cosmology. There are 2 ways to measure it. The first is the early universe method. You take the CMB data, fit them with your cosmological model, and extract the value of h0. The Planck satellite using this method gives h0 equals 67.4 kilometers per second per megaparsec. The second is the late universe method. You measure distances to nearby galaxies directly using standard candles like Cepheid variable stars and Type 1a supernovae, and you measure their recession velocities. This gives you a direct local measurement of the expansion rate, and the value you get from this method, most prominently from the SHOES team, led by Adam Rees, is about 73 kilometers per second per megaparsec. These 2 numbers do not agree. The discrepancy is about 8%, which might not sound like much, but given the precision of both measurements, it corresponds to a statistical significance of about 5 sigma. In physics, 5 sigma is the threshold for claiming a discovery. It means there is less than a 1 in 3.5 million chance that the discrepancy is due to random statistical fluctuation. This is not a minor disagreement. This is a major statistically significant tension between two of our best measurements of a fundamental cosmological parameter, and it has only gotten worse over time. As both the CMB measurements and the local measurements have become more precise, the tension has not gone away. It has grown. The James Webb Space Telescope has independently confirmed the local measurement using Cepheid stars and other distance indicators, ruling out many proposed systematic errors in the local measurement. The tension appears to be real. What does this mean? There are several possibilities. The first is that there is a subtle systematic error in one or both measurements that we have not identified yet. This is always possible, and scientists on both sides are working hard to find any such errors. But as the measurements have been cross-checked and refined, the room for undiscovered systematic errors has been shrinking. The second possibility is that our cosmological model is incomplete. The standard model of cosmology, called lambda CDM, assumes a specific set of components: ordinary matter, dark energy in the form of a cosmological constant, and specific physics governing their behavior. If there is something missing from this model, something that affects the expansion history of the universe, it could resolve the Hubble tension. Proposed solutions include early dark energy, a new form of dark energy that existed in the early universe and then decayed away, new interactions in the dark matter sector, additional relativistic particles in the early universe, modified gravity, and many others. Each of these proposals can reduce or resolve the tension to varying degrees, but none has yet emerged as a clear winner. The third possibility, which is the most exciting, is that the Hubble tension is telling us something genuinely new about the fundamental physics of the universe, something we have not thought of yet, something that requires a revision of our deepest theories. The Hubble tension is one of the hottest topics in cosmology right now, and its resolution, when it comes, could reshape our understanding of the universe. Now let me tell you about the CMB Cold Spot. This is one of the most intriguing and mysterious features on the CMB map. It is a region in the southern sky, roughly 10 degrees across, in the direction of the constellation Eridanus, that is anomalously cold. It is not just slightly colder than average. It is much colder than you would expect from the normal statistical fluctuations of the CMB. Its size and depth are difficult to explain within the standard cosmological model. The probability of such a feature arising by pure chance is estimated at about 1 to 2%, depending on how you define and measure it. That is not impossibly rare, but it is uncommon enough to warrant attention. Several explanations have been proposed. The most conventional is that the cold spot is a statistical fluke. With a 1 to 2% probability, it is unlikely, but not impossible. After all, if you look at a large enough sky and measure enough features, you will inevitably find some that are improbable. This is called the look elsewhere effect. However, many cosmologists find this explanation unsatisfying because the cold spot is really quite extreme. A more physical explanation involves a cosmic void. Observations of the galaxy distribution in the direction of the cold spot have revealed an enormous void, a region of space with much less matter than average, roughly 300 megaparsecs across. When CMB photons pass through a void in a dark energy-dominated universe, they experience a net cooling. due to the Integrated Sachs-Wolfe effect, which I will explain in more detail shortly. The idea is that the cold spot is not an intrinsic feature of the CMB, but is caused by the CMB photons passing through this supervoid on their way to us. This explanation is plausible and partially supported by data, but the calculations show that the supervoid alone cannot account for the full depth of the cold spot. It can explain part of it, but not all of it. And then there is the most exotic and fascinating explanation of all. Some cosmologists have proposed that the cold spot could be a bruise from a collision with another universe. In the eternal inflation scenario, which I will discuss later, our observable universe may be one of many bubbles in a much larger inflationary multiverse. If two bubble universes collided, the collision would leave a circular imprint on the CMB of the bubble that was hit. The cold spot has some features that are roughly consistent with such a collision, although the evidence is far from conclusive. This idea is speculative, and most physicists treat it with healthy skepticism. But it is not crazy. It is a legitimate scientific hypothesis that makes testable predictions, and it illustrates the kind of profound questions that CMB anomalies can raise. If the cold spot really is evidence of another universe pressing against ours, it would be arguably the most important discovery in the history of science. Next, the axis of evil. And yes, that is really what cosmologists call it. In the CMB, the large-scale patterns, specifically the lowest multipoles, which describe the broadest, most large-scale features of the temperature map, appear to be aligned with each other and with the plane of our solar system. The quadrupole and the octupole, the two largest scale features after the overall dipole, show an alignment that was first noticed in WMAP data and later confirmed by Planck. This alignment was dubbed the axis of evil by Kate Land and João Magejo in 2005. Why is this troubling? Because the CMB should have absolutely nothing to do with our solar system. The CMB was released 13.8 billion years ago, billions of years before the solar system formed. Its large-scale features are determined by conditions in the very early universe, conditions that are completely independent of where in the universe the solar system happens to be located. The alignment of CMB features with the solar system plane, if real, would be an extraordinary coincidence, some kind of unknown connection between the very large and the very local. What could cause it? One possibility is that it is a systematic error. Perhaps the process of removing foreground contamination from our own galaxy has introduced a subtle bias that aligns the residual features with the galactic or solar system plane. This is possible, but has been extensively tested, and the alignment persists even after aggressive foreground removal. Another possibility is that it is a statistical fluke. The large-scale features of the CMB are measured with limited precision, because there are few independent measurements at such large angular scales, something called cosmic variance. So the alignment might just be a coincidence, amplified by our tendency to notice patterns. But the probability of the alignment occurring by chance is estimated at less than 1 in 1,000, which makes it hard to dismiss. No satisfactory physical explanation has been found, and the axis of evil remains one of the most uncomfortable anomalies in CMB cosmology. Then there is the hemispherical asymmetry. When you divide the CMB sky into two hemispheres, one half has slightly more temperature variation, more power, than the other half. This asymmetry has been detected by both WMAP, and Planck, so it is not an artifact of a single instrument. The standard cosmological model assumes statistical isotropy, the idea that the universe looks the same in all directions. Hemispherical asymmetry violates this assumption. The difference in power between the two hemispheres is small, a few percent, but statistically significant, given the precision of the measurements. What could cause it? Proposed explanations include anisotropic inflation, where the inflationary expansion was not perfectly uniform, features of the pre-inflationary universe that affected the initial conditions of inflation, and large-scale modulation of the primordial power spectrum by some unknown mechanism. None of these explanations is widely accepted, and the hemispherical asymmetry remains an open puzzle. Finally, the lack of large-scale power. The CMB has less temperature variation at the largest angular scales, the lowest multipoles, than the standard model predicts. This was first noticed in COBE data, and it has been confirmed by both WMAP and Planck. It is a subtle effect, but it is persistent and consistent across all three missions. One possible explanation is that the universe is not infinite, but has a finite spatial extent, a closed topology. In a finite universe, there are maximum scales beyond which fluctuations cannot exist, which could suppress the large-scale power. This is a fascinating idea, but current data do not decisively favor a finite universe over an infinite one. Other explanations include modifications to the inflationary potential that reduce the amplitude of long wavelength fluctuations or simply cosmic variance, the inherent statistical limitation on measuring large-scale features. Now, I want to be honest with you about these anomalies. There is a real and ongoing debate in the cosmological community about how seriously to take them. Some scientists believe they are just statistical flukes, artifacts of the look elsewhere effect, and the inevitable quirks of random data. When you measure as many features as the CMB contains, some will inevitably be unusual just by chance. Other scientists believe the anomalies are real and point to new physics. The truth is, we do not know yet, and that is okay. That is science. Science is not about having all the answers. It is about pursuing the right questions. And the CMB anomalies, whether they turn out to be flukes or the harbingers of a revolution, are exactly the right questions to be asking. Now, I have to ask you something. Which anomaly do you find the most fascinating? The cold spot? The axis of evil? The Hubble tension? The hemispherical asymmetry? Drop it in the comments below. I genuinely want to know what you think. And also, tell me where you're watching from. I want to see if we have viewers from every continent. Yes, even Antarctica. Are there scientists at McMurdo Station watching this right now? Let me know. I love seeing how far this community reaches. Drop your location below. Let me now take you into a topic that represents one of the most exciting frontiers of CMB science, the search for primordial gravitational waves. This is the great quest of modern observational cosmology, and its success or failure could reshape our understanding of the very first moments of the universe. Gravitational waves are ripples in the fabric of space-time itself. They were predicted by Einstein in 1916 as a consequence of general relativity, and they were first directly detected in 2015 by the LIGO experiment, which observed gravitational waves produced by the merger of two black holes. That detection was a monumental achievement and won the 2017 Nobel Prize in Physics. But the gravitational waves LIGO detected were produced by astrophysical events, collisions between black holes and neutron stars, events that happened in the relatively recent cosmic past. There is a different kind of gravitational wave that is even more exciting and far more difficult to detect. Primordial gravitational waves. These are gravitational waves that were produced not by astrophysical events, but by the process of inflation itself. During inflation, the violent exponential expansion of space generated ripples in space-time, stretching quantum fluctuations in the gravitational field to macroscopic scales, just as it stretched quantum fluctuations in the density of matter. These primordial gravitational waves would have filled the universe, and like the CMB photons, they would still be reverberating today, though greatly weakened by the expansion of the universe. And here is the key. Primordial gravitational waves would leave a specific, detectable signature on the CMB. When the CMB photons were released at recombination, the gravitational waves passing through the plasma at that time would have left a particular pattern in the polarization of the CMB. Polarization is a property of light related to the direction in which the light wave oscillates. Imagine a rope stretched between two posts, and you shake one end. The wave that travels along the rope can oscillate up and down, or side to side, or in any direction. Light waves work similarly. The direction of oscillation is the polarization. The CMB is slightly polarized, and this polarization carries information about the conditions at the time of recombination. There are two types of polarization patterns, called E modes and B modes, named by analogy with the electric and magnetic components of electromagnetic fields. E modes are produced by density fluctuations and are relatively easy to detect. They have been measured by both WMAP and Planck. B modes are the prize. B-mode polarization can be produced by two things: gravitational lensing, which bends CMB photons as they pass through the gravitational fields of large-scale structures, and primordial gravitational waves. The gravitational lensing B modes have been detected, but the primordial gravitational wave B modes have not. Not yet. The detection of primordial gravitational wave B modes would be a monumental discovery. It would provide direct evidence that inflation actually occurred. It would probe physics at energy scales of about 10 to the 16 giga-electron volts, far beyond the reach of any particle accelerator, including the Large Hadron Collider at CERN, which operates at about 10 to the 4 giga-electron volts. It would test quantum gravity, because the primordial gravitational waves arise from quantum fluctuations in the gravitational field, which means their detection would be evidence that gravity has a quantum nature. In other words, detecting these B modes would be evidence that gravity, at some level, obeys the rules of quantum mechanics. This is one of the deepest open questions in fundamental physics. General relativity, our best theory of gravity, is a classical theory. It does not incorporate quantum mechanics, and every attempt to construct a quantum theory of gravity has been fraught with difficulties. The detection of primordial gravitational wave B modes would not give us a quantum theory of gravity, but it would provide the first empirical evidence that such a theory must exist. The strength of the primordial gravitational wave signal is characterized by a parameter called the tensor-to-scalar ratio, denoted R. This is the ratio of the amplitude of tensor perturbations, gravitational waves, to scalar perturbations, density fluctuations, If R is large, the signal is strong and relatively easy to detect. If R is small, the signal is weak and difficult to distinguish from noise and foreground contamination. Inflation comes in many varieties, described by different theoretical models, and these models predict different values of R. Some models predict R of about 0.1, which would be detectable by current or near-future experiments. Others predict R of about 0.01 or even smaller, which would require much more sensitive instruments. The current best upper limit from the combined Planck and BICEP data is R less than about 0.036. This means the signal, if it exists, is weaker than about 3.6% of the density fluctuation signal. Many popular inflationary models predict values of R that are just below this current limit, tantalizingly close to detection. There was a dramatic and cautionary episode in the search for B modes that I must tell you about. In March 2014, the BICEP-2 team, a group of scientists operating a telescope at the South Pole, held a press conference announcing that they had detected primordial gravitational wave B modes with a tensor to scalar ratio of about 0.2. The news was explosive. Headlines proclaimed that scientists had found direct evidence of inflation, echoes of the Big Bang itself. It was compared in significance to the discovery of the Higgs boson. The BICEP-2 team was celebrated. Some people started talking about Nobel Prizes, but then doubts began to emerge. Other scientists pointed out that the BICEP-2 team might not have adequately accounted for the polarized emission from dust in our own galaxy. Interstellar dust grains, tiny particles of silicate and carbon, are aligned by the magnetic field of the Milky Way, and they emit polarized radiation at microwave frequencies. This dust signal could mimic the B-mode pattern from primordial gravitational waves. The BICEP-2 team had used an estimate of the dust contribution based on preliminary publicly available data from the Planck satellite. But when the full, more accurate Planck dust data became available, it became clear that the dust signal in the region of sky observed by BICEP-2 was much stronger than the BICEP-2 team had assumed. A joint analysis by the Planck and BICEP-2 teams, published in 2015, concluded that the observed B-mode signal was consistent with being entirely due to dust, with no significant primordial gravitational wave component. The claimed detection was retracted. This was a painful moment for the scientists involved and for the field, but it was also a beautiful demonstration of how science is supposed to work. A claim was made. Other scientists scrutinized it. The scrutiny revealed a flaw. The claim was revised. Science self-corrected. No one was dishonored, no one was punished. The process worked, and the search continues. The BICEP program has continued with improved instruments, BICEP-3, and the BICEP array, using more frequencies and better foreground removal techniques. The lesson was learned. To detect primordial B modes, you need to observe at multiple frequencies so you can separate the CMB signal from dust and other foreground contamination. And you need to be very, very careful. The current status of the search is this. No primordial B modes have been definitively detected. The upper limit on R is about 0.036. But several major experiments are underway or planned that could reach the sensitivity needed to detect values of R as small as 0.001. These include the Simons Observatory, already operating in the Atacama Desert in Chile, CMB-S4, a next-generation ground-based experiment that will deploy roughly 500,000 detectors at sites in Chile and Antarctica, and LightBird, a satellite mission led by the Japanese space agency JAXA, scheduled for launch in the late 2020s. LightBird is particularly exciting because it will observe from space, free from atmospheric contamination, and it is specifically designed for B-mode polarization measurement. Its target sensitivity is R equals 0.001. If inflation produced gravitational waves with AR greater than about 0.001, LightBird should see them. And let me be clear about why this matters so much. If primordial B modes are detected, it would be one of the most important discoveries in the history of physics. It would confirm inflation. It would probe physics at energy scales 10 trillion times higher than the Large Hadron Collider. It would provide evidence for the quantum nature of gravity. It would open a window to the very first instance of the universe, far beyond the reach of the CMB itself. And if primordial B modes are not detected, even by the most sensitive experiments, that would also be profoundly important. It would rule out many popular inflationary models and force us to reconsider our theories of the very early universe. Either way, the science wins. Now let me take you into another dimension of CMB science, one that involves some of the most clever and powerful observational techniques in all of astrophysics. These are the secondary effects, processes that happen to the CMB photons on their long journey from the surface of last scattering to our detectors. The CMB photons do not travel through a vacuum. They travel through a universe that is filled with matter, with galaxy clusters, with cosmic filaments, with gravitational fields, and as they pass through these structures, they are affected. They are bent, boosted, cooled, and scattered. And these secondary effects carry their own rich cargo of information about the universe. The first secondary effect is gravitational lensing of the CMB. As CMB photons travel toward us, they pass near massive objects, galaxy clusters, concentrations of dark matter. The gravity of these objects bends the paths of the photons, just as a glass lens bends light. This gravitational lensing subtly distorts the pattern of the CMB. It does not change the frequencies of the photons or their total number. It changes their directions. It smears out the acoustic peaks slightly and introduces a characteristic pattern of distortion that can be measured. By measuring this lensing pattern, cosmologists can map the distribution of all matter between us and the CMB, including dark matter, which does not emit light but does bend it. This creates a mass map of the universe showing where matter is concentrated and where it is not. It is one of the most direct and powerful ways to study the distribution of dark matter in the universe. Planck detected CMB gravitational lensing at very high significance, and it has been used to constrain the amount and distribution of dark matter, the sum of neutrino masses, because massive neutrinos suppress the growth of structure, and the properties of dark energy. The second secondary effect is the Integrated Sachs-Wolfe effect, or ISW effect. This one is subtle, but profoundly important. When a CMB photon enters a gravitational well, say the gravitational field of a massive galaxy cluster, it gains energy, it blue shifts, and when it climbs out of the well on the other side, it loses energy, it red shifts. In a static universe, these two effects would exactly cancel. The energy gain falling in equals the energy lost climbing out. But in an expanding universe, the gravitational well can change while the photon is passing through. In particular, if the universe is dominated by dark energy, the gravitational wells decay. They get shallower over time. So the well is slightly shallower when the photon climbs out than when it fell in. This means the photon does not lose as much energy climbing out as it gained falling in. The photon emerges slightly more energetic than it entered. It gets a tiny energy boost. This effect, the ISW effect, has been detected by cross-correlating the CMB map with maps of the large-scale distribution of galaxies. Regions of the sky where there are many galaxies indicating deep gravitational wells show a slight excess of CMB temperature. This is an independent and elegant confirmation of dark energy's existence. The ISW effect tells us that the gravitational wells of the universe are indeed decaying, which only happens if dark energy is dominant, exactly as we infer from other measurements.